used for a lot of the retrofit assessments. So you put in all the details about your house, the U values of the walls and so on, and it gives you outputs such as how much heat demand is required. I mean, I guess with our house, it's not, the building fabric is not particularly good. And if you've heard, one key thing that a lot of people talk about is that fabric needs to be, you need to have insulated your house and reduce the drafts in order for a heat pump to work well. My experience here is sort of gives an example of a heat pump that works well in a house that hasn't had those things done to it. But it's not to say that I'm not trying to say that other people should do that. It's just the situation that that I was in this particular case. And I would like to go on to insulate the house and improve the building fabric. So the house is solid stone external walls. It's got a partially insulated ground floor, 200 millimeters of loft insulation, and some pretty poor double glazing. It's 76.8 meters square, so fairly standard size for a house, and the annual space heat demand there, that's a fairly standard amount. I guess if you were supplying that heat with a gas boiler, it would end up being something like 12,000 kilowatt hours a year or so of input gas. 126 kilowatt hours per meter square obviously is not great. If passive house is 25 kilowatt hours per meter square, and I think some of the other standards around 40 or 50 kilowatt hours per meter square. So to design the system, I guess to start with, I just wanted to see, what size system, if I could. I guess it was a bit of a question to start with. Well, did I definitely need to do the installation straight away, or was it possible to design a heat pump system that could be installed in the house in its present state, and then do work on the insulation and do the building fabric work as a second stage, and then have the same system continue to be suitable. So I guess to start with, I just went through the process of designing it for the house in its current form, and then I wanted to just see, how suitable would that be. So when you're doing a heating system design, you need to do a room by room heat loss calculation. So this is a little bit different from what you can do in the My Home Energy Planner software. You actually want to define each room in the house and the heat flowing to the external walls and to the other rooms in the house, and then you're trying to design a suitable size radiator for that room. So as for the entire house, and then the other part of doing a room by room heat loss calculation is that you're trying to work out what the heat demand is at the coldest point in the year. So it's there's a standard, I can't remember the exact percentage of hours that it is meant to cover, but your heating system should be able to provide enough heat, to deal with a condition that's -3 degrees outside, and to keep your house at 21 degrees on the inside, or in particular rooms like the living room. So doing that calculation on the house suggested we needed 5.5 kilowatts of radiator heat output. So if we just bear that in mind as we go through the rest of the calculations. So at 0 degrees, that would fall to 4,900 watts. At 5 degrees, which is more typical of the temperatures in January, that falls to 3,800 watts. So you could, for example, have a system that would supply enough heat to give your average temperature in January, and that's a fair bit lower than that extreme temperature. And I'll come back to that later, because that was a bit of a question for me when I was designing the system. As you'll see, I have undersized the system, and it doesn't quite meet that 5.5 kilowatts. And I was worried to begin with whether that would be, you know, the implication of that. So I decided to go down this route of doing the slightly smaller system with the view that I would later do building fabric work, and that we also have the option to have there's a backup very small wood stove that we could use as a backup. I'll come back to that later.
Can I say something here, or?
Yeah, absolutely.
Okay, because funny enough, I was faced with exactly the same dilemma. And in fact, I had an installer who said, oh, put an 11 kilowatt one in, or 8.5 or something. And I made the same decision you did and put a 5 kilowatt one in, and thought, well, because I've got a slightly larger house actually, and it's detached. But I thought, yeah, I'm going to insulate it and get it down to that. And actually it worked very well straight off, you know. So, yeah. And the other thing we know too is that heat pumps are very sensitive to being oversized. If you oversize your heat pump and it's turning off and on all the time, it's going to be really inefficient, and you don't want that. Yeah. Okay. So good to see.
Yeah, great. Thanks, Andy. So yeah, you've got these. I mean, heat pumps come in a varying level of options for sizing. You've got for the Mitsubishi EcoDan, which is one range of heat pumps. You've got the smallest one is 5 kilowatt heat output. Then you've got 8.5, and then you've got 11. So I guess if you look at this calculation to begin with, you see it's 5.5 minus 3. You'd probably go, okay, I need to be safe, go for 8.5. But I'd known from my experience with monitoring heat pumps and working with John Cantor, who's been advising me with all of this, and he's sorry to jump about a bit. John's a very experienced heat pump engineer who's been working in the field for 30 plus years, and I initially started working with him to help him with some monitoring work, and then through that started to get an understanding of these different systems. And he's always been keen. He's always recommended going for the smaller system, and it's the way you use it, you can get good results from that. I know there's different viewpoints on this, so I might try and come back to that later. Maybe we can come back to that one later. So anyway, I decided to go for the 5 kilowatt system, and that covers the majority of the conditions I'm going to see. So everything up from 0 degrees, and quite comfortably the kind of temperatures you see in January as an average. So this is looking at the floor plan. This is where I've put the radiators in the house. So we've got two quite large ones in the living room here. I don't know if you can see my mouse. I don't know if that comes through. So the living room is the part of the floor plan here on the left. Downstairs, it's open plan through here. So we've got two 1,200 millimeters by 600 millimeter radiators there. And then we've got another one here by the back wall of the dining room, and we've got another one here in the hall. So these are just standard double panel radiators from Screwfix. Then on the first floor, there's a larger radiator in the bedroom, in the two bedrooms, the study, and quite a small one in the bathroom. And the heat loss calculation actually said I needed a much bigger one in the bathroom, but we didn't really have the wall space there. And I just thought I'll put the smaller one in for now. If it's a problem later on, I can always revisit this and put a larger one in, or think of another solution.
Can I ask why you put the radiators under the windows?
Those were, so there was, sorry, I missed one thing at the start. So there was already the heating system that was in the house before was a back boiler on a wood stove, well, on a coal stove, and it really didn't work at all. If you tried to use wood, it just wouldn't get any heat. And so there was already a system in the house, and we reused some of the pipework for that. So for the radiator in the downstairs, the back of the dining room, for example, that's reused pipework, but with the sort of ends of the pipes extended to cater for a larger radiator. And the same thing for the two in the actually the one in the back one in the bedroom, bed one, that's on the same, that's on the kind of old pipework. The others, the other two in the front, bedroom 2 and study, that's all new pipework going to those, but it's just the walls that made the most sense, in a sense, in terms of not being in the way. I moved, the old system had a large radiator in the downstairs living room window, and I moved that to the side here. So that was one position that I moved. So obviously when you're designing, a key thing about a heat pump, to make it work well, is that you want to have the flow temperature of the water as low as possible. And so normally with a gas boiler, you're running the system at 70 degrees or so. And so you need relatively small radiators in each room. But with the heat pump, ideally you want to get down to 30 degrees mean water temperature. And the heat pump will emit much less heat at that kind of flow temperature. So you need to oversize your radiators, or have underfloor heating, so on the right hand side here, you can see that if we wanted to get to 21 degrees Celsius in the living room, in the main living area, and the mean water temperature was 40 degrees, the system as designed here would provide 4.5 kilowatts. And that dropped all the way down to 1.8 kilowatts at 30 degrees Celsius. If the rooms are a little bit cooler, the radiators are able to get rid of more heat, And so here at 30 degrees, the radiator emits 2.2 kilowatts. So the system as designed, again, I've undersized the radiator system, which is not great. It would be better to have a larger, it would be better to have more surface area of radiators or underfloor. Ideally, if you were designing it to give, it's worth bearing in mind when we talk about the performance later, that if this system was designed so that it could provide 4 kilowatts or 5 kilowatts at 30 degrees Celsius, the whole thing would perform even better than the results that I have got out of it. Yeah, I'll come back to that a bit later. So then the other thought was that, again, with the intention of improving building fabric, a smaller system, could make sense, because later on, with better building fabric, the radiators would be plenty sufficient to provide those hotter temperatures, indoor temperatures at a cold outside temperature. So here's just a very quick overview of the equipment. So there's a 5 kilowatt EcoDan. These are the material costs, which I think are quite interesting to reflect on when you think about the total cost of a typical system. I was very fortunate in this case because I was working with John, and he's gone through a lot of this with me before. So I was able to do a lot of the work myself with him acting as an advisor. So I was more aware of these material costs than you would otherwise be. So the heat pump is 2,400. The new radiator is about 500, and the cylinder there about 900. So total cost around 4,500 for the materials. So this is here's the I've had it in now for about 1 year and 4 months, but towards around December this year, I wrote a blog post just describing, going into detail on what the performance was in the first year. So if you copy that link, you can read about it in more detail. But essentially, the first surprising thing was that we used 45% less energy than I'd calculated we should use in the assessment for the house. And then the second thing was that we got really good performance from the system. So, an average space heating coefficient of performance of 3.96. So that's 3.96 units of heat coming out of the system for every unit of electricity you put in. And a little bit lower for water heating, because of course, you're heating water to a higher temperature. So, you get less. The performance of a heat pump is very, essentially there's the physics equation for it is the Carnot equation, and the performance is a function of what the outside temperature is for an air source heat pump and the temperature of the flow water coming from the heat pump. So the higher that flow temperature and the colder the outside temperature, the worse the efficiency, or the closer together, the better the efficiency. So I was very pleasantly surprised to get nearly 4 from the system, given what I'd heard elsewhere about the performance of other systems. I think the Energy Saving Trust did a a field trial of heat pumps a number of years ago now, and the average coefficient of performance for air source heat pumps was something like 2.48. So, you know, a lot lower than what I've got here. And at 2.48, at the time, the grid carbon intensity was you know, much higher than it is now, and then the carbon emissions of the heat pump, as it were, you know, the heat delivered was similar to that of gas, but yeah, or you needed to get above 3 to really beat gas. But today, with the much lower carbon emissions or carbon intensity of the grid, that's changed quite a bit. But at a COP of 4, it's even better. So the actual heat that we delivered per meter square there was 69 kilowatt hours per meter square, which, you know, is a lot less than the 126 in the assessment. And so I wanted to work out, you know, why had I used so much less energy to heat the house than I'd you know, calculated in this assessment. And the main reasons, I think, well, the two main reasons are that the external temperatures were a little bit warmer than those assumed in SAP. So it was that accounts for about 8.3% of that difference. 8.3% out of that 45% less energy, as it were. So this is this green stacked chart on the left here. So the other big contributor was that we actually ran the house a fair bit cooler than the SAP assumptions. So rather than having the living room at 21 degrees when it was heated, we had the house at about 18.5 degrees. So obviously that's going to make a big difference to why we'd use less energy. But it goes to show that you can, you know, that there are other options you can put a jumper on to get those lower, that lower energy consumption. So then there's another fairly sizable chunk there that's coming from some other source. And one possibility is that the U values for the stone walls is better than you know, the standard U values suggested. And there is some work that's been done on that by Historic Scotland, which came out with similar results, showing that stone wall U values could be a fair bit better. I mean, they're still really poor, but better than the values that were the standard values in SAP, as it were. So that could account for another part of it there. So the electricity because we use you know, that, because we managed to reduce the amount of heat that we put in, and we got that good space heating performance, because we got that good COP, the actual electricity we ended up putting into the house was relatively little for space heating. So it was only 1,276 kilowatt hours, which would have been about 200 quid for the year. And that's, interestingly, that's 5% less than the average electricity consumption for space heating in the sort of average house in zero carbon Britain. So even though we have this really poor house in terms of building fabric, we were able to achieve results that are, you know, we weren't using a prolific amount of electricity, as it were. So I thought I'd show a screenshot of the internal temperature in the house. Yeah, this is in the December of 2019. So this is an example of us running the house, the average temperature there is pretty cool at 17 degrees. So obviously that might be a bit cold for a lot of people. You'll notice at the heat pump's going on and off, every day we're turning it on for a certain number of hours every day, and so the temperature is swinging accordingly. When during the heating period, we are often above 19 or 18 to 19 degrees is especially from December 13 onwards here. We were quite comfortable with that temperature and just put it on as we felt we needed it, really. So the outside temperature was 6.3, and we were by no means running the heat pump continuously. We were running it at about 20% of capacity, so we could have run it much more, and we could have got that heat. We could have got the internal temperature up a fair bit more. We could have actually put twice as much heat into the house without increasing the flow temperature. So the flow temperature is that key thing for the performance. And we could have put in a lot more heat had we increased the flow temperature, and to a detriment to the performance, and run it longer. But it meant we were very much within safe margins in terms of the heat pump's operation. We could have run it for longer. We could have increased the temperature if we did feel too cold. So now in January 2020, unfortunately didn't quite make it into that blog post because I finished it in. We had a little addition to the family, so it was therefore very important to have a higher internal temperature in the house. So as you can see here, the average internal temperature is now 18.9 degrees in January. The outside temperature was a little bit warmer at 6.5, and we put in a fair bit more energy to achieve that. So in December we put in 800 kilowatt hours of heat. And in January, we put in 1,200 kilowatt hours. So we increased, that's a fair increase. And it's now, that's still, it's now much closer to that SAP figure of 1,400 kilowatt hours. So that shows, that a large part of the reason for the lower consumption in the previous year was because we were running the house cooler. So even running the heat pump, even achieving this higher temperature, the COP remained surprisingly actually at exactly the same COP of 4. The flow temperature was a little bit higher, so it was 1 degree higher than in December. But the heat pump was now running for 32% of the time. Sorry, the heat was now a capacity, so it could have. So it's using a bit more of its capacity, but still plenty of room there. When we run the system at 30, we are actually running it at the minimum heat output of the unit, and it's a little bit less efficient on the minimum value, and it does get a little bit, there is a kind of trade-off between the minimum compressor speed or the minimum heat pump output and the flow temperature in terms of the actual COP that you get. So you could actually increase it by 1 degree when it's running at the minimum, and you may get better results. But if I took that up to 35 or 38 degrees, it wouldn't. You'd really see that COP drop then. So in January, I ran the heat pump 80% of the time at 500 watts of electrical input. So it was running most of the time. Whereas in December, we only ran it 54% of the time. So I think another interesting thing about using heat pumps is these new tariffs, and it's really expensive between 4 and 7, but it's generally very cheap otherwise. As you know, it's down to about 5 pence per kilowatt hour in the overnight, but up to 25 to 30 pence per kilowatt hour at the peak time. So I was a bit concerned that obviously with the heat pump I would still need that heat through that peak time, and I was a bit concerned that that might lead to high costs. But actually, in looking at because you're using, because I had the heat pump on for a large part of the day, the average price was actually quite low. So here, for example, in January, the average price from Octopus Agile to supply the heat pump would have been 10.6 pence per kilowatt hour, which is pretty cheap, really. And that works out to 2.6 pence delivered heat, which I think gas is about 3.5 to 5 pence, isn't it? So it's pretty cheap. It can be very cheap if you're on this kind of tariff and you use it in this particular kind of way. Obviously, if you just turn on the heat pump between 4 and 7, it's going to be very expensive. So that's the end of my slides. I think I'll probably just open it up for questions. There's probably 101 things I forgot, yeah, there's a lot of detail to this stuff that I probably skipped over a bit quickly. So feel free to ask any more basic questions, and you go back to the start, and yeah, happy to answer any questions on that.
So there's a few questions in the chat, Tristan. I don't know whether it's worth just starting off with them.
Okay.
So Dom asking whether the 21-degree spikes were the wood burner or whether that was the heat pump. And Kate asking how much of that heating was coming from your neighbours as a mid-terrace, and is there any way of working that out?
Cool. Okay. So yeah, for the wood burners, the wood burner. Let me see. Okay. Yeah. So these very high spikes here is the wood burner going on. Yeah. And there's 2 spikes in January. So there's 2, and they were the actual amount of heat that we got over the last year. The total amount of heat from the heat pump was 95% of our heat requirement, and 5% was from the wood burner. And we've had it on less this winter, January onwards. Obviously, pretty keen not to use the heat pump as much as I can, not to use the wood burner as much as I can because of air quality issues. Though I don't think none of our neighbours take any notice of that, unfortunately, because there's just billowing coal smoke most days from one of our neighbours. But yeah, it's, you can see, yeah, that's what that is there.
Oh, they're coming in thick and fast now, actually. So we've got Paul Tanner asking if you had any issues with siting the pump, in terms of planning rules or anything like that, because I know you're also in a very beautiful part of the world, so that may cause issues. And did you have any, and how did you size the tank? Have you sized it for an expanding family with daily baths?
Yeah. I'll just go and answer Kate's question about the temperature from the neighbours.
Oh, yeah. Sorry.
What temperature are they at? Well, I think of looking at, just try and move this here. So I think I can account for a large part of it being the internal temperature and the external temperature being higher, internal temperature being lower. So basically that, I guess it looks like just under 1/3 of that difference could come from other sources. And that could well be heat from the neighbours or more solar gain, or so that's definitely a possibility that there is some heat contribution coming from the neighbouring houses.
Okay, we've got Ken pointing out that party walls should be included in SAP's heat calculations. So what about the size, the siting of the pump? Paul Tanner's question. Any issues with that?
So the heat pump is mounted on the back wall of the house. So this is it's mounted on a bracket just below the bathroom window. So it's designed to meet the the noise. You have to make sure that you don't exceed a certain decibels of noise at your neighbours' windows that they might be occupying, such as a bedroom or living room. So that, we did that calculation carefully. That was fine. I think otherwise it doesn't need planning permission to put it in that area. For sizing of the water tank.
Yeah, go for that.
Yeah, so I put in 150 litres, which may be a little bit on the small end it was definitely on the small end for a heat pump cylinder. So normally you're looking at 200, 250, 300 litres. And I was thinking, well, I don't really want to be heating a huge amount of water and need unnecessarily. But yeah, we do now go through that tank pretty quickly. It is sufficient, but we've gone from having one heat up a day to doing 2 heat ups a day, just so because of giving the little one a bath in the evening and then having enough for a shower as well. Yeah, certainly. That works fine as long as you do, doing 2 heat ups works pretty well, really. So the cylinder is 150 litre unvented cylinder. It's not a thermal store, and that's certainly one of the things that you'll come across when designing a heat pump system, or when you discuss one with an installer or so on. So this is one of John Cantor's recommendations, essentially, that you can get quite a bit better performance with just a normal cylinder in this configuration. But there are good reasons for thermal store, such as improved Legionella protection, but it does mean that you have to get the water in the store to a higher temperature than because you're then transferring that heat from the store to the water that's going through to your shower or to your taps. So it needs to be higher than the water temperature at the shower. Whereas with the cylinder, you can actually heat the cylinder up to the temperature that you need for the shower, and then put it straight through to the shower. You still have to do the Legionella protection as well.
So Kate asks, how quickly does it heat up?
The hot water tank?
Yeah.
It takes about, so if you go flat out, so at 5 kilowatts, well, the cylinder is basically about, if you're heating the cylinder up from cold, it takes about 6 kilowatt hours of heat. So, and the heat pump has a 5 kilowatt output. So it takes, just over an hour from cold. So that's your water in the cylinder being at 15 degrees, say. Although if you're doing 2 heat ups a day, then it might be 2 half-hour heat ups, that kind of thing.
And we've got David Brook asking if you can say something about, in terms of the metering graphs you've shown, how much of that is from the heat pump's own sensors and how much is from sensors that you've retrofitted yourself?
Yeah, sure. So I haven't shown a huge amount here of the monitoring that's involved in this. So it's all our open thing. The actual, so to get a COP figure that I could feel confident saying, this is high accuracy, and because even a small inaccuracy in the electricity measurement or the heat measurement can throw your COP figures out by a long way. So on the electricity input, I've got an Elster billing grade meter, so that's 1% accuracy, and on the heat side, I've got a Somtex flow meter, which is quite an expensive piece of kit, so it's about 350 quid, and that gives you billing grade heat measurement on the output. That then talks to the graphing software, which is called eMonCMS, which is the stuff I work on most of the time. There's a piece of hardware that reads the data from the heat meter and from the Elster electricity meter, and then takes that and records it and allows you to do the graphs and so on. And then these internal temperature graphs, this is all our room temperature and humidity nodes. So I've got little sensors in every room, just to record the average internal temperature.
So Jonathan's asking if you got any RHI on this installation.
No,
Yeah,
I didn't go. Obviously, I didn't go down the RHI route because I did the installation myself. I did look into initially when we were looking at the different options. I got a couple of quotes for getting the heat pump installed and getting RHI, and it was too much for our budget. It would actually work out to being about the same over 7 years, because obviously you get the RHI and that would pay things back. but you'd start off having to spend a very much larger amount of capital. And I was really keen to learn really about the installation, learn a bit of plumbing in the process, and obviously having John Cantor's expertise to guide me through along the way. That was something that was an option for me, although maybe I shouldn't have taken it on in terms of the time involved.
So just quickly, because I think we will probably hand over to Andy after a couple more questions, and then we can all get back together again afterwards. So Paul Tanner was asking what your approach was to avoiding expensive power, which is a bit like a question I asked in there as well, about whether you'd looked at any sort of automation to reduce heat pump, to reduce your activation of the heat pump when in response to electricity prices going up.
Yeah, so I was thinking with that, with the Optimus Agile tariff, that you could turn it off over that more expensive period in the evening. So I experimented with that a bit, and you can definitely do it some times of the year, but other times the temperature just drops too much, and you start to feel it. And so we just found just running it at a low level was fine. Although you're still using expensive power, because you're using a lot of power, you're using power at a cheaper rate at other times of the day. The average is quite reasonable. So I've become less worried about using that more expensive power for a few hours, given that the average works out. But certainly, if that would be something that I think would be more of an option, or that become more of an available option, if we externally insulated the house, because then we'd have all that thermal mass that would keep the house warm through those hours. So we could then, because the walls would just stay warm, they would keep the temperature of the house at a much more stable level. I did some modeling on that, and it does look like it would be a really feasible approach, and I should be able to then turn it off for quite long periods and keep a good internal temperature.
That's great. So there's a few more questions which I think Ken has actually dealt with quite well in the Zoom chat. So if you feel your question's not been answered, just have a quick check in there. Has anyone else got any burning questions before we hand over to Andy Hamilton? Looks like not.
Maybe I'll just say, I guess this example is imperfect in quite a lot of ways. So one, the house isn't, the building fabric of the house is not great, and then two, it's a radiator system, and it's a little bit undersized. So it's not exactly, your best example, as it were. But it does show that if you can keep the flow temperature low at around 30 to 32 degrees, you can get very good performance from the system. Obviously, insulating and improving the building fabric is really important, because then you can reduce the total energy consumption further, in a significant way as well, and you potentially get these other benefits, such as being able to turn the system off through those expensive times. I guess the key thing was being aware of the importance of keeping that flow temperature low, running the system for a longer period of time to account for that lower heat output, that lower flow temperature and lower heat output. So we'd need to, for example, if we were both working out from not in the house in the day, and you come back at 6 o'clock, I'd need to start the heat pump in the middle of the winter. I'd need to start the heat pump at just after 1 o'clock in the afternoon. So it would need to run for 5 hours beforehand just to bring the temperature up. So obviously that might feel that sort of intuitively feels very wasteful, because there's a system running there for 5 hours when you're not in the house, but it's running at a very low power level. So it's running at 500 watts of electrical input, 2 kilowatts of heat output. Whereas when you heat the house up very quickly, before you come home with a gas boiler, you're putting in 12, 15 kilowatts of heat. You're really you're driving that temperature up quickly. It does actually use a little bit less energy to do that, because obviously if you keep the house at an elevated temperature, it loses more energy. But for a heat pump, if you try and boost the heat with a heat pump, you actually end up using more energy still. But there is a balancing point there. It's quite hard to get at exactly where that is. But I mean, that's just an example of the kind of thing that we did to get the performance to be that high.
And then we've got two last things, which is Catriona asking how much insulation is on the tank. Is that just as it came, or have you done any interventions with it? And Rosie asking if we can get your slides by email. We can distribute them if you're happy to share them.
So what was the first question?
Yeah, how much insulation is on your hot water tank?
75 millimeters on the hot water tank.
And have you done that yourself, or was that just as it came?
That was as it came. So the cylinder was from Newark cylinders, and they do a kind of design. They do like a cylinder to order, and you basically specify the kind of heat pump coil you want, and the size of the cylinder, how much insulation, where you want the connections, and so on.
Right.
So Ken says there, you design system for worst conditions, so all of the time. Yeah, so that's an interesting point. So in theory, I could run the system at a lower temperature at the shoulder months of the year, but one of the limitations with a heat pump is that you can only it's got a minimum power level, as it were. So with this one, the minimum power level is 500 watts of electrical input and 2 kilowatts of heat output. I could, if the heat pump could modulate down further, you could actually drop that flow temperature even lower and get even better results. But the actual, because of the way that my system is designed, it can't do that. There is a way you can do that. So that's where buffer cylinders come in. So I don't know if people have heard of the. So with a buffer cylinder, you can essentially heat that buffer cylinder at a lower flow temperature, but at a higher heat output level, and then you can sort of cycle a buffer through the system. I had a chat with there was a heat pump engineer on Twitter who was sort of pointing this out to me, that I could get much better performance, and he was getting COPs of 5 and 6 with his systems designed in this particular way. So I mean, and that's, in a way, you can see where his point is coming from, because I'm getting a COP of around 4 with radiators slightly undersized, with a heat pump just going at the minimum at this with this undersized radiator system, if I had, you know, underfloor heating, potentially a buffer cylinder, then I could actually drop that flow temperature even further and provide the same heat and get even better results still. But I guess I'm pretty happy with the results that I have got. I think a COP of 4 is quite respectable.
Tristan, don't underestimate what you've done. Getting 4 out of a heat pump system is really good. The best one, I think, on the TSB report that you mentioned earlier, I think was about 3.5, and as you said, the average was about 2.5. So one thing I can say about your talk is that in a way you've been a bit modest, because actually it's a good achievement, and also it works and it's economic. And yeah, you can play about with all these things, but one of the things is that if you run the heat pump on a low power, 500 watts or whatever, well, actually it's not so efficient, is it? I think when you go down like that. So yeah, that's it. All sorts of things you have to look at. One other issue, I think, for me, which perhaps we can have a conversation about some other time, is running it on the thermostat or running it. I just run mine for so many hours a day. I just say it's going to come on for 2 hours and it's going to turn off, and I set it to do that. I don't run it on a thermostat, because when I was on a Mitsubishi field trial, it showed me that people who run it on the thermostat and had the thermostat set up all wrong, so it was coming on and off every 10 minutes or something, they had efficiencies down about 2 or something, you know, COPs. The other thing, can I just say a little bit about heat pumps with carbon co-op? Is it the appropriate time, Matt? Or
please do, Andy. Please do.
Right.
Have you got anything to share in terms of presentation stuff, or do you, or
not now? That comes later.
Okay,
so
sure.
What I want to tell you about is there is, as Jonathan said, there's this thing, I think on the 24th of June, the guy from Tipperary, who will present what they've done in Ireland, which, excuse me, when I looked at it, seemed a lot better than what the UK government stuff was in 2016. I haven't looked at the later stuff. So that should be interesting. What we're planning to do is, after that, on the week after that one, 1st of July, I want to give a basic introduction to heat pumps. So actually, Tristan's done a good introduction anyway, but I'll do that probably for people who aren't part of this group, but are part of Carbon Co-op generally. Mm-hmm. And then the idea is that after that, we want to roll out several other sessions. Tristan, this might catch you by surprise, but we're hoping that you were going to do 1 or 2 sessions on your system, right? This would be sometime sort of towards the middle of July, after I'd done an introduction, and then I would carry on and do something about getting an installer. I actually used an installer. I'm not as clever a plumber as Tristan or John Cantor. However, before I got an installer, I spent a lot of time talking to John Cantor, and I recommend to you his book here. It's called Heat Pumps for the Home by John Cantor. And if you want to take details, it's the Crowwood Press, and I think it's 2011. Yeah, 2011. So a great book if you want to get into heat pumps and, you know, get the basics. Yeah, so that's the general rollout for heat pumps. We were discussing it this afternoon. I was discussing it with Jonathan and Polly from Carbon Co-op. So it's all fairly new. You should see it coming out and publicised. But as I say, Wednesday evenings from the 24th of June, there's a good chance there'll be something about heat pumps. One of the things that I'm going to cover in particular is if people want to think about their own heat pump system and think about getting an installer in. Incidentally, installers can vary a lot, but I'm going to talk about that, how you avoid the installers that are just there for the money or whatever, and get somebody who is good. And that's an issue. The other thing I would like to say in sort of summary of, sorry, the lighting's going a bit funny. That's the other computer coming in. The other thing I'd like to say in summary was that for heat pumps especially, beyond any other heating system, calculating the heat you need and getting that right, and then monitoring the system and then tweaking it according to what your information is coming back is really important. And that's how you avoid getting efficiencies of 2.5 and get your efficiencies up to the type of stuff that Tristan has managed with his system. I'll talk a little bit about my system, which actually has a lot of similarities to Tristan's in terms of where we run the systems at a low temperature between 30, well, I'm between about 30 and 35. And, you know, slight differences, like I don't have a buffer tank because I've got underfloor heating. So the concrete is the buffer tank, as it were, which forms the underfloor heating. And I have got a system because I put an extension on the side of the house, and essentially I've got a 28-ton storage heater now, where, because mine's a stone-built house. Well, anyway, I'll go through those details. I shouldn't be getting into that now. But it does make a big difference that you can choose really when you want to turn on your heat pump. Okay, yeah, apologies for the light show, folks, and thanks again, Tristan, for that presentation. It was good stuff.
Thanks.
Okay, so
thanks, Andy.
We've got, yeah, we look forward to that, Andy, and you'll see from the chat that there's quite a lot of appetite for that, particularly around how to select installers.
Yeah, that's difficult. I'll tell you the story about how I made a mistake to start off with, but luckily remedied it. Really, anyway, I'll give you the details later, another time.
I think Ken is an installer. I read on the chat.
All right. Okay. Well, good. I mean, be interested to talk to him actually. So, Ken, if you're there, if you want to email me, andyham@gmail.com, it would be good to talk.
Okay. All right. Excellent stuff, everyone. So, so if we just want to, we normally with EcoHome Lab sort of open it up for anyone else who has anything to present this month. So I don't know whether anyone would like